Good morning, good afternoon, and good evening. I'm your host, Aya Takase, and I'm here with our presenters, Dr. Pierre Lapmagueres and Dr. Eric Reinheimer. Thank you for joining our webinar. We call this one, Think You Can Afford a Single Crystal Diffractometer? Meet the XtaLAB Mini 2. So today, we also have our special guests, Professor Claire Besson from Binghamton University, SUNY, and Professor Jason Halfen from the University of Wisconsin at Eau Claire. They will provide their perspectives as the XtaLAB Mini users. So if you always wanted your own single crystal diffractometer, but the cost kept you from it, you might be pleasantly surprised. Pierre will be introducing an affordable benchtop diffractometer, the XtaLAB Mini. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window. And we'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. And please submit those questions via the Q&A button at the bottom of your screen. And we will not be monitoring the raise the hand function. And we'll try to answer as many questions as we can during the live webinar, and we will respond to any unanswered questions by directly contacting you after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. Okay, with that said, I will turn it over to Eric.
Well, thank you very much, Aya, and I would like to welcome all of our attendees to this webinar. Before we get started, kind of in furtherance of what Aya said, I want to ask a couple of questions. Have you really investigated in great deal the cost that it would take to introduce chemical crystallography to your lab? Is this cost a dollar amount that might be hard for you to secure? Well, the great news is that you're in luck. With this webinar, we're going to be discussing today the XtaLAB Mini 2. And the great news is that from the low hundred thousands, you can bring research level instrumentation to your lab, all with a benchtop form factor. So we very much hope that you find this webinar informative, and we look forward to communicating with you and answering any questions towards the end. And with that said, Pierre, the floor is yours.
Okay, thank you, Eric and Aya. Hello, everyone. Welcome to today's webinar that will indeed showcase the XtaLAB Mini, our benchtop X-ray diffractometer. And right away, let me show you a live feed of the XtaLAB Mini. I'm standing right here by the system because we are basically live from the applications lab at Rigaku in the Woodlands near Houston, Texas. And then let me step in front of the camera right now, real quick, to say hello to everybody. So you see the XtaLAB Mini sitting here on the desk, so in the corner of our lab here. So we're ready to go. So indeed, the XtaLAB Mini is a benchtop system, and as such is also our most affordable one. But right away, the question is, does it still collect good enough data suitable for a publication? So we'll try today to convince you that indeed the XtaLAB Mini does collect high quality X-ray crystallography data that fulfill the IUCr requirements for publication. Yeah. And really, as such, we see the XtaLAB Mini as the perfect opportunity for you to acquire a single crystal X-ray diffractometer that will allow you to publish crystal structures, even if you have a reduced budget. So later during this webinar, I will also run a live demo of the system. And for that purpose, I have already mounted right here a crystal of cytidine. So cytidine is an organic compound, one of the standards usually used to evaluate X-ray diffractometers. So it's almost ready to go. I just have to center it. And for that matter, we will also use our program, the Crystallis Pro, which is our X-ray data collection program and data reduction. So I'll show you the gist of that interface in a few minutes as well. So for now, let me go back to the view of the XtaLAB Mini. And so let me show you that I'm closing the door and locking the door by pushing this yellow button that is currently blinking. So I need to lock the door for the shutter to open up and collect data. So otherwise, so nothing will data collection will not kick on. So that prevents me from being accidentally exposed to the X-ray beam. And in the same vein, during data collection, I cannot open the door. I cannot even unlock it. I have to abort data collection from the program first, and then only can I unlock the door. So really, this is a safe and secure system to be used even by beginning students. So now let me get back to my presentation. And now that we've set the scene, we would like to start by posing you a polling question so that we know a little bit more about our audience today. Aya?
Okay, thank you, Pierre. So we wanted to ask the audience a question before we get into the details. And the question is, do you plan to acquire a single crystal diffractometer in the next 12 months? So your choices are yes, and I haven't approved the budget. That's good for you. Or yes, but I have budget limitations and challenges. Or you might say no, or I don't know. So answers are coming in pretty fast. I'm going to give you a few more seconds to think about it and choose your answer. About half of them are in. I guess I'll wait a few more seconds. And maybe people are thinking about it. Okay, so I'm going to close the polling in 3, 2, 1. And I'm going to share the results. Nobody seems to have approved the budget, but some are thinking about it. And actually, half of you said, I don't know.
Okay, good.
Okay.
Well, I mean, this is the point of such a webinar also to show people what they can, what is available to them really out there and what they can afford. Okay, cool. So continuing on now with this presentation, I would like to start with a generic slide that shows the whole panoply of X-ray diffractometers that exist out there on the market, allowing crystallographers to solve crystal structures. So if we start from the left-hand side, of course, with the XtaLAB Mini benchtop diffractometer, and then going from left to right, we jump through the microfocus seal tube systems, and then the microfocus rotating anode, and all the way to the right here to synchrotron beam lines. And of course, as crystallographers use these different systems, they use stronger and stronger X-ray beams, and therefore they can afford to analyze smaller and smaller crystals. Now, there's a consensus that says that once you hit a crystal dimension of about 1 micron, you hit some kind of a wall, meaning that X-rays are no longer really strong enough to generate data or enough data from a sub-micron crystal in order to solve the crystal structure. So that's when people turn to electron diffraction, as indeed electron diffraction, as shown on this picture at the bottom right, electron diffraction can analyze data from submicron particles enough to actually solve crystal structures. But again, this is not our topic today. Our center of interest today is the XtaLAB Mini. And to explain the performance of the XtaLAB Mini, I will use the following agenda today. In the first part, I will actually go over the hardware that makes up the XtaLAB Mini so that I can actually explain to you how we managed to build a diffractometer that is good enough to collect data for publication while remaining affordable. In the second part, this is when I will run a live demo of the system with that crystal of cytidine. And then I will also give some real-life examples of crystal structures solved with data collected on the XtaLAB Mini. And in the last part, we will review the labs, institutions that we think can most benefit from the XtaLAB Mini. And this is also when Professor Halfen and Professor Besson will intervene and tell us why they acquired a XtaLAB Mini and how it helps them in their research, and they will do that in their own words, of course. All right, so first part then, let's go through an overview of the hardware. And I want to show you first, or give you first some of the general, how to say, specifications of the system. So you have the width, depth, and height of the system right now on your screen, and the weight of about 220 pounds, which means about 100 kilograms. In terms of installation and safety and maintenance, you saw before on the video feed that it can sit on the desk, and then as a result, you can certainly put it in the corner of the lab. It really doesn't take much space. So it also comes with its own water cooling device that is used to temperature control the source. And usually you will actually slide that chiller underneath the desk on which the XtaLAB Mini sits. As I explained also a couple of minutes ago, there is no possibility for accidental X-ray exposure. So you are completely safe and secure there. And now in terms of maintenance, so really minimum maintenance is required. Okay, so the tubes last several years. In our experience, between 3 and 7 years, more or less on average. So the detector works in ambient conditions. So the detector does not need to be cooled down. There is no vacuum chambers in the detector either. Therefore, no pumps, no seals, no nothing, right? So no maintenance there either. And lastly, you will see in the next slide, there is no possibility of hardware collision of the goniometer. So that all really keeps the maintenance at a minimum level. One last remark before I move on to the next slide is that the XtaLAB Mini is also compatible with the regular cryo systems that you've got out there. Those cryo systems that you can usually set on bigger, fancier diffractometers. The same can be added to the XtaLAB Mini. Now, you can purchase the cryo system at the time that you are purchasing the XtaLAB Mini as well, or you can add it later. It's up to you. There's no problem there. Okay, so now here is a view of the belly of the XtaLAB Mini, really the actual goniometer. And let me start with the source that resides in that conical compartment on the left-hand side here of the picture, highlighted with an orange rectangle. So the source is a fine focus seal tube that generates a flat X-ray beam with a diameter of about 5 microns. And the radiation is that of molybdenum. The monochromator is a curved graphite monochromator. And the goniometer here, so this is, on the goniometer, there are only 2 axes that rotate. And that's why I said on the previous slide, there is no possibility of hardware collision. That's because you only have 2 axes rotating. So there is phi and omega. Phi is the axis that runs along the axis of the goniometer head, and omega is the horizontal axis on this picture, and this is the data collection axis. So data is being collected along omega, and omega can rotate up to 180 degrees, with phi rotating throughout 360 degrees. Now you see that bend here. Maybe I can switch on the pointer option for my cursor here. You see the bend here in the omega arm. So that bend represents the chi angle, okay? And chi is fixed at the so-called magic angle of 54 degrees to optimize completeness of data sets. Last but not least, the detector here on the right-hand side of the picture, the detector is fixed as well. It's fixed at the 2 theta angle of 20 degrees and a distance of 45 millimeters. So with that detector position and the moly radiation, we can collect data up to 0.7 angstrom resolution on the edge on one edge of the detector. So repeat, up to 0.7 angstrom resolution data collected on that detector. A little bit more information about the detector, because we think this is a big deal here in the sense that we have a hybrid photon counting detector within that little guy, that little XtaLAB Mini. So it's called the HyPix Bantam. So photon counting is the same technology as most of the detectors that you find at synchrotron beamlines. So there you have it. You basically have a synchrotron technology for the detector inside the XtaLAB Mini. And that technology really features lots of advantages, including high sensitivity. Very important, it does not generate any electronic noise. So on your diffraction images, the background is made of the scattering background from everything that sits inside the beam and of the electronic noise. So obviously, if you remove one of these two components, namely the electronic noise, now your overall background on the images are is lower. The I over sigma statistics are better, and of course, you can catch more of the high resolution weak reflections because now you're gonna be able to see them better. Because you have no electronic noise, there's no need to collect a dark current image before data collection like you do with CCDs, for instance. The active area of the detector is about 8 centimeters by 4 centimeters, and its pixel size is 100 microns by 100 microns. So I'm done with the overview of the hardware, and we thought that we would take a little break here and maybe ask Eric whether any questions have come out already. I can certainly ask a couple of questions now.
Well, yes, we do have one question so far. Can the crystalLab Mini 2 analyze MOFs?
The answer is yes, to certain MOF samples. So bear in mind that the beam comes from a seal tube system, not seal tube source, not microfocus. So therefore, the beam is weaker, and this is the Molly radiation, which makes also the flux weaker than if it was a copper beam, right? Nevertheless, so if you have a fairly, and I'm emphasizing on just fairly well-behaved MOF crystals, then yes, you will be able to collect proper data on the crystalLab Mini. But for those MOF crystals that are tougher, diffracting fairly weakly, then you are starting to push the envelope here when you use the crystalLab Mini. Okay, so this is maybe when you have to go to using a stronger beam, but that's understandable, right? We have here a benchtop system that we kept at a lower price, and therefore the most difficult samples, meaning the more weakly crystals, will not be adequate for this system.
Oh, fantastic. Thank you, Pierre. Another really good question related to the hardware is the monochromator an equivalent of the shine optic or a successor?
No, it is. That's a very good point. This is actually a shine optic, curved graphite shine monochromator. Yes.
Fantastic. And one last question that has come in. Can the crystalLab Mini analyze twins?
Yes, that's a resounding yes as well. Keeping in mind one thing again is which is the molybdenum radiation. The molybdenum radiation being fairly short, so reflections are closer together, which may be a problem when you have a twin, but that you would have the same problem on a bigger diffractometer if you use the molybdenum radiation also. Okay, so yes, you will be able to analyze twin crystals. Some of them will be more difficult because of the molybdenum radiation, not because of the system, because of the molybdenum radiation.
Excellent. Well, thank you, Pierre. I think we're good for now, so
yep,
we can keep going.
Okay. So part number 2, let me show you what the crystalLab Mini can do. And so here I will switch back to showing you the interface of our data collection program and showing you what the crystal actually looks like. So on purpose, I didn't center it, so I can center that crystal right away or quickly in front of you by making it come to the crosshair here. And you will have an idea of the size of that crystal also. So this is the height of the sample, obviously. Now let me center it along the x-axis. Of course, going the wrong way first, as always. There it is. Maybe adjust the height a little bit more. And now rotate by 5 by 90 degrees to have a side view of the crystal and center the crystal in that second direction. So the blue circle you see on the screen represents a diameter of 200 microns. So right there, you can see that the thickness of the crystal is about 100 microns. And in the other two other dimensions, about 200 microns, not quite, by another 100 microns. So again, let me adjust that a little, and so that's maybe a little more adjustment here along the horizontal axis, and we'll be good to go. All right, I'll stop there. Close the door, lock the door like you saw me do a few minutes ago, and then I get out of there and I will start collecting data. So the first thing to do is to, of course, screen the crystal, push the button Start Stop at the top right here of the interface, choose a new project. And so our screening process is really a two-step endeavor. So the first step is just a quick screening of the crystal. It takes a few X-ray images of the crystal for visual check as to whether the crystal diffracts, and if so, how. What do the reflections look like? Obviously, here I've chosen a crystal that I know works. So I will jump to the second step right away at the bottom right corner of your screen and run the pre-experiment. Okay. So the pre-experiment collects more images in 3 different crystal orientation. I will set up an exposure time that I know works for that crystal. And then, then I push the button pre-experiment. And so in a few seconds, we will see the first diffraction reflections appearing on our screen. So if you look at the top right of your screen, you will see that the shutter just opened up, okay? And our reflections start appearing on the screen. At the bottom left of your screen, there's the run number and the frame number that are being recorded. So the first scan, or each scan, is made of 10 frames. So we have collected already frame number 7. And so now in a few seconds, the first run will be done. The shutter will close. And if you look at the bottom, yeah, it was a little bit too fast, but so now the goniometer is actually moving. Actually, you can see phi moving now, rotating to 90 degrees at the bottom left of your screen. Phi is now at 90 degrees to collect a second run of data on the crystal, with the crystal in a different orientation. And that second orientation of the crystal is orthogonal to the orientation it had in the first scan. And then there's going to be a third scan or a third run, yet again with an orthogonal or different orientation of the crystal. If you look at the top right part of your screen now, you see that an automatic indexing is ongoing. I'm not doing that. Crystallis Pro is doing that automatically. And so right there, you can see that Crystallis Pro does a lot of things automatically already, which is very comforting for beginning crystallographers. So Crystallis Pro will get you to, will do several things, go through several steps automatically and get you to a good starting point. Now, don't get me wrong, you can redo everything manually, okay? But Crystallis Pro will help you, especially if you are a beginning crystallographers. And then also a little bit like on the right hand side, on the more or less mid height, you see an area that says strategy. A data collection strategy is already being calculated behind the scenes because we have a unit cell already. We already have an orientation matrix as well. So we might as well start collecting or calculating a data collection strategy. And now that the whole screening is complete, the proper data collection strategy interface opens up with a strategy ready to go. Okay, so that was all calculated again because automatic indexing was being performed behind the scenes. So right now, Crystallis Pro tells me that it wants to collect 618 images in 5 different scans or 5 different crystal orientations. With the exposure time that Crystallis Pro estimated would be good for that crystal, at the top right here, I highlight an exposure time of 15 seconds. The whole thing would take about 3 hours. And Crystallis Pro based its calculation of the exposure time on a target I of a sigma that we set up in the program. So we want a target I of a sigma of at least 15 for the data data collection strategy calculation. So for the sake of this demo, I will reduce the exposure time to 5 seconds. So now I've got about 50 minutes of a data collection time for the purpose of this demo. Okay, so the only thing I've got to do now, oh, sorry, one thing I want to mention before I actually start the data collection. Let me not jump the guns here. You always want to have a look at the diffraction pattern in the reciprocal space, and there's an easy way to do that here. If I push the lattice wizard button, and then the reciprocal space viewer button. And this is a view of the diffraction pattern in the reciprocal space, which I can orient along either one of the three reciprocal space axes. So if I orient the view along A star is now perpendicular to the screen. With the right mouse, I can zoom in and out. And so now you can see that those reflections coincide with the crossing points here on the lattice, or also called lattice points. And of course, you want as many reflections to be to coincide with the lattice points as possible. The last thing I'm going to say here is that the size of those circles is proportional to the intensity of the reflection. So here is the view of the reciprocal space along A star, along B star, and along C star. And here everything checks out just fine. I'm going to close that interface, go back to the strategy interface, re-enter the exposure time I wanted to use, 5 seconds, and off we go for data collection. So I'm going to push now start named experiment, give a name to the crystal, which will allow Crystallis Pro to create an additional or a data folder with the name that I give right now to the crystal. And now I'm also entering the chemical component of that crystal. Now, why do I do that? You might wonder. Well, that's because Crystallis Pro does not only collect data, but it also reduces the data and tries to solve the structure, all that during data collection. So Crystallis Pro to solve the crystal structure uses AutoChem, which is an automated version of OLX2. And OLX2 itself runs its own structure solution and refinement program, or you can plug in the ShellX executables as well. So as long as you have a program trying to solve the crystal structure, you might as well help that program by giving it the chemical content, or at least the chemical elements that you think are in your crystal. Okay, so that's what I did here. I push start, and now the data collection will start momentarily. The first thing that Crystallis Pro does, though, is take live pictures of the crystal. I'm going to cancel that for the sake of time for this demo, but just know that Crystallis Pro takes pictures of the crystal throughout 360 degrees along phi, and those pictures are used afterwards to do phase indexing. Yeah. So here again, I've canceled it so that we don't waste too much time waiting for those pictures to be taken. So now the goniometer is bringing itself into position to start the collection of the first images of the first run or the first scan. So shutter just open as shown by the red button at the top right of the corner of the interface, and now diffraction reflections start appearing again on the screen. So on the bottom left, I'm showing you again the run number and the frame number that is being recorded. When the first 25 images will be recorded, Crystallis Pro will start its automatic data reduction. And then after every batches of 25 images, Crystallis Pro will reprocess the entire data set and again, and so add up to the completeness of the data sets. And of course, calculate all the scaling statistics as more and more data comes in. So of course, we will not sit here waiting for these 25 images to be collected. We will come back to this interface in a few minutes, but for now, let me go on with the actual presentation. So while data is being collected, let me show you a very few examples of crystal structures solved with data or from data collected on the XtaLAB Mini. So that first example is that of chlorothiazide. It is an organic compound. And I chose that example because chlorothiazide crystallize in the lowest symmetry possible, P1. There is no symmetry in that crystal, not even the center of symmetry. So that means that there is no symmetry-related reflections. All the reflections are unique, which means that you have to collect all the reflections that come out of the crystal. And therefore, more reflections to collect, more or longer data collection time. So that's why I chose that example. I want also to point out the dimensions of the crystal, you see that the thickness of the crystal is only 60 microns, so it's not big at all. And then the other two dimensions, about 100 microns. So that data set was collected in just 6.5 hours. So this is the merged completeness, right? This is not the anomalous completeness. The Friedel pairs have been merged here to yield a 99% completeness at 0.8 angstrom resolution. And the structure solution yielded an R1, a good R1 factor of basically 4%. So first example with a P1 crystal. Second example with another low symmetry crystal, P bar 1. So now at least we've got a center of symmetry within the crystal, but again, a very thin crystal, 40 microns. Okay? So this is a data set that was provided to us by Professor Gerlach from the University of Wisconsin at Eau Claire. As you can see on the right-hand side, so that compound was also an organic compound. It's a salt of perchlorate, and adding to the fun, the perchlorate anions were, of course, disordered. Okay. Data set, or the data was collected in 17 hours. So if you think about it, this is just an overnight data collection. Again, 99% completeness to 0.83 angstrom resolution. And the disorder of the perchlorate anions could be properly modeled, and the whole thing yielded an R1 just below 6%. So really nothing to be ashamed of at all. Third example, that crystal was really tough. This is a crystal provided to us by Professor Sandra Sekaran from Lamar University here in Texas. P bar 1 crystal again, thin crystal, 40 microns, but you see also, you can kind of see that on the picture of the crystal here, that there are streaks in that crystal. It was not a single crystal. That's what the diffraction images looked like, elongated and split reflections. And that's what the diffraction pattern looked like in the reciprocal space. It was absolutely awful. Okay. Plus weakly diffracting crystal, because overall the quality of the crystal was poor. Nevertheless, we didn't give up. We did solve the structure. But it took like 39 hours of data collection. So you see, I'm not showing you easy manufactured examples here. I'm really showing you tough examples. And this one here, a very tough crystals, took 39 hours, so a day and a half, but we did get the structure. And the R1 ended up at basically 7.5%. And that was collected at room temperature also. That R1 would have probably been a little bit better if we had used a low temp. But very difficult crystal. It's still a structure solved. If that's going to be the case for many crystals that you analyze on Crystal Mini, if you give it longer to collect the data, especially for the weak crystals. The last two samples are of much easier crystals. So organometallic crystals. So this one is a nickel coordination compound, again provided to us by Professor Sandra Sekaran from Lamar University. P2 upon N space group, but again, a thin crystal of 40 microns. Okay. Now, because of this is an organometallic compound, so data or diffraction was much stronger, data collection much shorter, so below 3 hours of data collection. Virtually 100% completeness at 0.8 angstrom resolution, and a beautiful structure just below 4%. Okay. Another organometallic compound or coordination compound of nickel provided to us by Professor Lisa Barrow from Utah State University. You see the crystal structure on the right-hand side. Beautiful crystal again, larger crystal though, right? But low symmetry, and data collection completed in just 2 hours. 99.2% completeness, 2.8 angstrom. Beautiful structure of with an R1 at less than 3%. So I just showed you a couple of or a few tough examples, but you see that as soon as you have a good-ish crystals, within a couple of hours, maybe a handful of hours, you will get your crystal structure. Okay, so now let me have a quick look. So you see I'm running a cooking show here. This is back to the Chrysalis Pro interface. If you look at the bottom right, you see that we've collected 27.8% of the full data set already, with a good R-int of 2.2% at the moment, 2.83 angstrom resolution. But I wanted to show you that, see, that this part of this data reduction again has taken place automatically while I was showing you these other examples in my presentation. So data reduction happening automatically in Chrysalis Pro, and here is another pass from Chrysalis Pro right now that you just saw. All right. once more back to my presentation here. We have a web page on our website dedicated to the publications that mention data collected on the crystalLab Mini. And if you go to Google Scholar and type these keywords, crystalLab Mini, you will see that 1,190 results come out. So that's quite a lot of publications from data collected on the crystalLab Mini. All right, I'm reaching the last part of my presentation here, and part of that last part is for us to reflect a little bit as to what labs and universities and institutions we think can benefit most from the crystalLab Mini. Of course, everybody who has a restricted budget, right? So you might think that you can't afford a proper single crystal diffractometer. Well, hopefully now today we can convince you that you should not give up and you should consider a benchtop system like the crystalLab Mini. It is affordable and it will collect X-ray data that you can publish. Number two, you may be in an institution that, where you have no access to crystallography expertise locally. Most likely you are, for instance, a synthetic chemistry lab and you need a local crystallographer, or you need a crystallographer to solve your crystal structure. If you don't have one, you may have to send your crystal to a third-party institution. But then, of course, you have to wait and you don't know how your samples are handled. So maybe at some point, enough is enough and you want to take control. So again, to start, even if you don't have crystallography expertise yourself, to start learning crystallography and to start becoming a crystallographer, the crystalLab Mini is so easy to use and so safe that it is a good tool for you to start with. And then you'll see throughout your career, you can progress and buy bigger and bigger diffractometers. But the crystalLab Mini is really a good system to start with. And lastly, I wanted also to mention teaching institutions. The crystalLab Mini is a great tool if you want to just teach crystallography to your students. Of course, to do that, you don't need a fancy and expensive diffractometer. Let's not forget the fact that bigger diffractometers are also intimidating, and students are more afraid to use them because, well, of course, they don't want to break it. So being so much smaller, the crystalLab Mini is not intimidating at all. We notice that students are jumping on it or using it easily. And so we guarantee you that everybody will love the Mini for as a teaching tool. Okay, so I think now it's time to give the floor to our special guests, Dr. Claire Besson and Dr. Jason Halfen. And I will start with Professor Claire Besson. Again, like Aya mentioned earlier, Professor Besson is from Binghamton University, SUNY, chemistry department there, and she's been the happy owner of a crystalLab Mini since April 2024. So it's still fairly recent. So Claire, go ahead. The floor is yours for a few minutes.
Hi everybody. So yeah, I've been at Binghamton for about 2 years. I'm a coordination chemist. We do synthesis of transition metal and lanthanide complexes for various applications, including magnetism, separation science, and a few other things. And before I came to Binghamton, there had always been an X-ray diffractometer available to us somewhere. I never owned one. I was never the crystallographer, but there was always one we could use at the institution I was working at. And so when I arrived at Binghamton and there was not one, I figured we needed to do something. Now with startup money, which was not great, SUNY, the Rigaku Mini it was. And since we've had it, myself and my grad students, who are the primary users of the instrument, have measured about 40 structures or thereabouts for ourselves and for some collaborations we developed within the university. The grad students, and now we are training some undergrads, have measured everything from uranium complexes to 2D layered materials to small molecule organics. We've been fairly happy with that. We've got 2 publications already coming out that were only made possible by having the instrument. So that's a pretty good experience. Has brought in some collaborations, which is nice. The biggest challenge we've had, I guess, was to measure a very thin needle that was maybe 20 by 20 microns in cross section. Was twinned, was the only one crystals our collaborator could make of that compound. Had some PF6 disordered. It took us a week of acquisition, but that is, submitted, accepted for publication as part of a larger paper, and we were very, very happy with it. For that one, we didn't even use the cryo we have. You can see the cryo on the picture just above Alex's head, one of the grad students. We've used it a couple of times, but for most of our structures, we found out that we get just fine results without it. And since refilling is a bit of a pain, we don't usually bother. And that is it for us.
Yep. Thanks, Claire. I mean, 20 microns by 20 microns. We'll see what Jason says, but that's got to be the record, right? That's really, really small. And I think it's important to emphasize once more, right, that you have most of the use of that system is from your graduate and undergraduate students, right?
Correct. I had not personally used an instrument much before, so we all started more or less at the same level. I had more experience in the general technology, but not on ever really using an instrument except a couple of times as a grad student. And so we all learn, and now the grad students are using it. We're training some undergrads. It works like a charm.
Cool. All right. Thanks, Claire. Jason, your turn. Floor is yours.
Thank you, Pierre. Yeah, so first of all, let me just say I'm happy to be here today and to provide you with some of the the insights that we've had here as a user at Eau Claire. So our experience kind of complements what Claire has at Binghamton. We have a longer term relationship with our Mini. So ours has been installed now for 5 years. We are a strictly undergraduate institution, so all of our users are undergraduate students and a couple of faculty as well. We're actually a significantly higher volume shop than Claire's is. And so this morning I started sample number 602 for our 5-year period. So if a person just kind of does the math there, we're putting together, 120-ish samples per year for 5 years. And so we put a fair amount of sample pressure on the instrument, supporting both research groups that are in-house, a couple of external collaborators, and it also has a very strong teaching component that I'll sort of get to in a little bit. Before we bought the Mini, our department had gone through a couple of point detector instruments, which we use strictly for research use. We really had an interest in bringing that crystallography more broadly to our students, but it was going to be hard with an instrument that can take 3, 4, or 5 days to do a single sample. So the Mini was perfect for us, and now we have it incorporated not only into our research programs but also into a fair amount of teaching use as well. For us, it's a really powerful instrument. So we don't have any 20 micron samples. Claire, you win the prize there. But over the 5 years, the Mini has probably handled, well over 95% of our samples. The very few samples that are really, really tiny, we shop out to somebody else for a rotating anode or something like that. But the vast majority of everything we've done in our entire department for 5 years has been handled by the Mini, and almost all of those are room temperature, much like Claire noted. And we do have a low temperature device. I think we might have used it once a year for the 5-year period. As I mentioned, we use the Mini not only for research, but also to support teaching. And so the interface is so easy, the instrument is so robust and safe that we run a large number of undergraduate students through that instrument, just like we would teach them to use our high field NMR. And so in our senior level capstone laboratory, all the students that are enrolled, that's 15 this semester, get experience determining all of their own structures. Those students determined 10 structures just this week, and we're only halfway through Thursday. And so this is something that is a significant component of their training, just like taking an IR, taking an NMR. Hey, let's crystallize that compound and get a structure too. Now we have a complete picture of what's going on with that compound. The other thing we really like is the low cost of ownership. And so as I said, this is the beginning where we've had it in the department for 5 years. we're still using the original tube. So even though we're putting through 600 samples in that 5 years, we're still on the same tube. We haven't had any major service calls. Virtually everything that has sort of come up with the instrument, we're able to get on the phone with our friends at Rigaku and get those problems worked out over the phone. And so it's really a very economical solution for us that makes us a more complete department and makes our students better trained to go on in the next steps in their careers.
Right. Thanks a lot, Jason. So you may not have the record for the smallest crystal, but you probably have the record for the highest amount of crystal structures. I mean, when you said 600, I mean, in 5 years, I mean, and 120 per year. So that's a crystal every 3 days, really, right? So that's nonstop. That's impressive. So I mean, I couldn't believe it. All right, excellent. So I think, Eric, we are ready for some more questions. And by the way, so the three of us, myself, Jason, and Claire, we can all answer your questions, okay?
Absolutely. We've got some more questions, and then depending on how much time we have, I'm going to put you on the spot, Pierre, in a very positive way. In a very positive way. So first, the first question of this section, what sources are available and how easy is it to change them?
Okay, so only one source available, only molybdenum. And only how to say fine focus. So we'll see how this product evolves, of course. But right now this is a fixed configuration with a fine focus molybdenum seal tube as the source.
Wonderful. What is the largest unit cell parameter that can be measured with this system when you consider the fixed sample to detector distance?
Yep.
So that you can avoid reflection overlap.
Yep. So I want to say, so now I have to dig into my memory, but I want to say that we've done a few samples that were about 35 angstroms in, oh, Jason. Okay, so then go for it, Jason.
Oh, I was just going to add, Pierre, that just this week, one of my students had a primitive orthorhombic sample with a long dimension of 42.8 angstroms.
Okay, 42. Okay. Oh, wow. So
and the spots were easily resolvable on the detector, no problem.
Okay, yeah. So and primitive, right? So that all the reflections are there, no extensions, right? So right. Yeah. So then, of course, that depends on the crystal itself, the mosaicity of the crystal, and so on and so forth, right? How large the reflections coming out of the crystal might be. So that's why I think pretty routinely 30-35 angstroms, and in certain cases you can go to about 40-ish angstroms, like Jason just mentioned.
Okay, wonderful. Can it analyze air-sensitive samples?
Sure. So for that, you just have to switch on the cryo system, right? And it's exactly the same story as on any other bigger diffractometer. You need to switch on the cryo system so as to protect the crystal mounted on the goniometer from ambient air. That's all. But that's got absolutely nothing to do with the XtaLAB Mini. It's the same on all types of diffractometers. So yes, it can.
Okay. We don't have much crystallography experience in my lab, if any. What kind of support does Rigaku offer for beginners like us?
Yeah, so and probably Jason and Claire can each say a few words about that also. But so I mean, when we install a system in our lab, so we just don't install it, train you, and bye-bye, right? So this is really the beginning of a relationship. We'll give you full training on the hardware and software. So we have training videos, and then we'll follow up with about 1 day of online training. That's number one. Number two, we can connect with you, of course, all kinds of email support. Number two, we can remotely connect with you via TeamViewer at any time to help you with the data set, with the data collection, with the strategy, with indexing, with looking for the twin law, with processing, no problem. Of course, if we are available, right? But if we are, we can connect with you at any time via TeamViewer at no cost, no questions asked. And number three, you can always send us your most difficult data sets also. We'll see what we can do with them. And if we can do better than you did, then we'll remotely connect with you again via TeamViewer and explain to you what we did so that you can also learn from what we just did on your data set and crystal structure. So this is really the beginning of a relationship, but maybe no pressure. But if Jason and Claire want to add something, be my guest.
Yeah, well, when we got the instruments, effectively, Lee Daniels was also on that call. Apparently, did the training for us, and
yes,
2 of my grad students attended. And effectively, after that, they were independent on the instrument. I still look when they've got some weird data at the little level that I can do, but they could solve, measure and solve most of the structure of the crystals they made.
Yeah, and I'm happy to add that. So we have a little bit of an embarrassment of riches here in that in my department, we have 2 trained crystallographers with service lab experience, myself and Dr. Gerlach. And so when we acquired the Mini, the 2 of us were able to really hit the ground running really fast because, of course, we had familiarity with a lot of what was going on with the instrument. What we've really benefited from during that 5-year ownership period is the ability to hop on TeamViewer with people like Pierre or Eric or some of the other staff at Rigaku, because occasionally we do bump into a situation where we have questions about a sample, we have questions about a lattice, and the staff has been incredibly helpful and supportive of everything that we're trying to do here. And so it's certainly been a big benefit to us as long-term owners of the equipment.
Good, right. Thank you both then for that.
Well, thank you very much. I have a question just that nobody else has asked, so I'll go ahead and ask it of you, Pierre. Can you do temperature-dependent data collections on the XtaLAB Mini, very similar to you would do with like the Synergy S or even a larger
Yep, absolutely.
system?
So with the program being exactly the same on all our systems, so the answer is yes. And Chrysalis Pro is very easy to set for a set of variable temperature experiments. So like the expression I use sometimes, like that my grandmother probably could set up those such a set of experiments. So of course, no time for me here to show it here, but you calculate the data collection strategy and then link that collection strategy to a set of temperature set points, going up and down and back up or whatever you want to do, and off you go. So Chrysalis Pro will collect each data set and change the temperature automatically in between data sets without any user intervention. So you can certainly set up a series of experiments for the weekend, and on Monday morning you end up with 50, 100 data sets, whatever, and then that are, by the way, already processed and hopefully the crystal structure solved as well. So yes.
Wonderful. And now with the last few moments, Pierre, I just want to put you on the spot as a very experienced crystallographer who's kind of seen a lot.
Yeah.
With your time on the XtaLAB Mini, could you maybe regale us of a tale of maybe the most difficult sample you've done?
Yeah, but I still can't beat Claire's story, but a similar story of a very thin organic crystal that the molecule only contain carbons and nitrogens, and very, very thin blue plate. It was so thin that it was flapping in the air like that. Right? So it took me 60 hours. I started Friday night to collect the data, and so came back to the lab Monday morning. The data was collected, or there was maybe like an hour left or so. So 60 or 62 hours of data collection, and I had an R1 of 4%.
Incredible.
So yeah, no. So this is so if you give it a little bit more time than a bigger, fancier diffractometer, the XtaLAB Mini will do a lot of crystal structure for you, sir.
That's wonderful. Well, I mean, we're out of actual questions, but
okay,
don't hesitate to our attendees. If you have any questions, please feel free to email us, and we'll be happy to answer those questions by email. But without further ado, we have to figure out just how does our data look that you started for us, Pierre. So could you go ahead and show that to us?
Yeah, so there it is. So it's structure solved here. We've collected so far 79.4% of the data up to 0.83 angstrom resolution. We've got an R int of 3.7%, and I have a sigma for the merged data of 17. Remember that I cut the recommended exposure time a little, but the structure solved here at the moment, we've got an R1 of 6%, I'm sorry, 5.5%, but this is to 0.7 angstrom resolution. So if I cut that to, let's say, 0.8 angstrom, I would go below 5% here, and the data set is not complete yet, so no problem. All right, so I think we're done here, I suppose.
Yeah, I have no other questions that have come through, and
Okay.
that means you've just done a fantastic job, sir. And so we really appreciate your clarity in this presentation, and it was just wonderful. So thank you for that, and thank you to our esteemed guests who've come to regale us of their tales with the XtaLAB Mini. And
yeah, really, Jason and Claire, again, thank you.
Yeah, thank you. Okay. Let me put one more thing in the chat. And so as I said earlier, a recording of the webinar will be available tomorrow, and an email will go out to all registrants with a link to the recording page. And the presentation slides you saw today, they are linked on the recording page, and you will find all the resources I shared in the chat as well. And if you're now curious and want to see if the XtaLAB Mini fits your budget, please request a quote from our website. I just put a link in the chat. You can just click it, and that will take you to a form, and you can fill it out and request a quote. Okay, well, thank you very much for joining us, and we hope to see you at the future webinar series. Thank you.
Bye, everybody.
Bye.
Thank you for
Thank
your
you.
attendance.
Thank you.